Welcome to the History of Science seminar series, second one this year, for the second year. It is a distinct honor and pleasure to introduce today's speaker, Christopher Phillips. He received his PhD in the history of science from Harvard University. He then received a postdoc at NYU, where I had the joy of interacting with him for a number of years. After NYU, he accepted a position at Carnegie Mellon University, where he currently resides as an associate professor of history. His research and teaching focus on the history of science in modern America. His first book, The New Math, A Political History, published with the University of Chicago Press in 2015, examines the rise and fall of the controversial new math curriculum with which I grew up against the challenging politics of mid-century America. He shows that far from being insulated from politics, the teaching of mathematics was framed as and understood as a fundamentally political enterprise. His second book, Scouting and Scoring, How We Know What We Know About Baseball, which just appeared in March, was it? 2019 from Princeton University Press. It's a great book, and I say that as someone who loathes baseball, all right? The work uses a collection of data in professional baseball as a way of exploring the supposed distinction between objective numbered knowledge and subjective people knowledge. He argues that data of both kinds are neither abstract nor natural, but grounded in concrete technologies and created only through the labor of many highly trained individuals. Chris is currently working on a history of statistics in medicine, tentatively titled Number Doctors, Health, Statistics, and the Reformation of Modern Medicine. It centers on a group of biostatisticians at the National Institutes of Health and their efforts to transform measures of causality and proof in medicine through the development of novel statistical measures from the 30s to the 70s. It is, in a sense, the prehistory of our current moment of risky medicine and precision medicine, as well as of algorithms and artificial intelligence in medicine. In this project, he asks how and why medicine became a science of numbers, and indeed, this is what he will be speaking about today. His title, The History of Biostatistics and the Origins of Precision Medicine. Please join me in welcoming Chris to IAS.
Thank you, Miles. With an introduction like that, I should have spoken about baseball. But nevertheless, I want to thank Miles Jackson for the invitation and Gabriella Hoskin for her logistics help getting me here. And as he intimated, this is indeed very much work from an ongoing project. So I look forward to your thoughts, your questions, and your feedback. Going to the doctor, I would argue, is an essentially numerical experience now. You might feel fine when you show up, but if some number is in the wrong range, you're not going to be fine when you leave there. If you develop a new drug, you might think it works, but you still have to show its effectiveness in at least 2 randomized clinical trials. If you're a physician who has a new protocol that you want to implement, you better conduct a meta-analysis of the published literature on this particular matter. And in some ways, this situation is quite odd historically. Clinicians, as opposed to, say, epidemiologists, until very recently didn't much care for statistical evidence at all. They dealt in things like aggregates, not in singularities. They didn't want to talk about the average patient and whether the average patient would get better. They wanted to talk about their patient and whether she would get better in this particular case. So in 1930, it was quite rare, not unheard of, but rare, to have statistical figures in academic medical journals. By 1980, it was essentially required to include those figures. And in my wider project, I'm looking at how this shift happened over a relatively short period of time, not just as a side element of what might be called medical reform, that is from the perspective of the doctors, but as actually an episode of its own in the history of numbers and statistics. And we already know this transformation has some very well-documented and important effects. So for instance, Robbie Aronowitz has written about risky medicine, which Miles alluded to. And indeed, he's talked about how being at risk for disease and having a disease are increasingly almost the same experience. Of course, others are not so worried about this transformation and actually have found a great deal of hope in it. So for instance, the evidence-based medicine pyramid, which you don't need to read, I can just tell you, the higher you up are on the pyramid, the more statistics you have in your particular reasoning. And the development of precision medicine over the last 20 years or so, at least in its coining, where you don't develop drugs for diseases, you develop drugs and treatments for individuals. These both treat the rise of numbers in medicine as a fundamentally positive story, as one that has made it more rational, more objective, more reasonable. And of course, I'm not the first historian of medicine to notice this transformation of numbers over the course of the 20th century. Indeed, Harry Mark's groundbreaking Progress of Experiment focused precisely on how medical reformers in the early 20th century allied their reform efforts in the mid-20th century with those of statisticians. Laura Bothwell has written on the history of clinical trials and controversies about them. William Rothstein has written about the history of public health and about the idea of risk factors within it. And Jeremy Green has traced quantitative changes in how we define diseases. In fact, once you have a good drug for high blood pressure, you might actually want to redefine what counts as problematic blood pressure, because the number of people you can then sell your drug to increases dramatically. And the story told by these historians so far is that clinicians continued to draw on statistical evidence, because it helped minimize bias. It helped control inevitable variations in outcomes between patients. But problematically for me, none of them actually take the statistics themselves all that seriously, which is to say that they act often, not always, but often as if medical researchers are drawing established tools off the shelf, a kind of fixed set of techniques that they can then deploy. And of course, the statisticians themselves sometimes play into this, saying all we're doing is applying common sense, because they want their statistics to be treated as if it was just common sense, ready to be applied. So if the development of biostatistics, of this kind of statistics for biology, is one answer to how this larger transformation in medicine happened, I think we need to know a lot more about this field, about the people in it, about the connections between universities and institutes like the National Institute of Health. And I think what we'll get from doing so is that we'll move past the old saw that medicine will become scientific when doctors learn to count, that kind of traditional idea of science and medicine. And instead, we can be able to talk a little bit more about how statisticians developed tools and they developed techniques precisely suited to the exact needs of clinicians and government regulators at mid-century. In short, what I want to talk about is what do we get when we put biostatistics back into the history of medicine. Biostatistics is a very odd discipline in some ways. For instance, it's not really mathematical statistics in a kind of formal way. It's also not really vital statistics in traditional public health terms of morbidity, mortality. It's not really biometrics in a Galton-Pearson eugenical sense from the late 19th, early 20th century. And it's also not really epidemiology in dealing with prevalence rates. It draws from all these fields, but I, at least in my kind of preliminary work, would argue that it's distinct from these, and we should treat it as actually a distinct field. To be concrete, today I'm focusing on this handsome gentleman, Jerry Cornfield. It's one small slice through this material, but Jerry is, I think, a very good way to go through the material. Cornfield was one of the first statisticians hired at the NIH in 1947, and within a decade, he was the inaugural head of the first biostatistics department at Johns Hopkins. And so a very quick transformation. Later, he headed up the statistics effort at the National Heart Institute. When he was originally hired, it was at the National Cancer Institute. We'll talk a little bit more about that. And later, he was president of the American Statistical Association, the American Epidemiologic Society, and he was vice president of the American Heart Association. Not bad for a guy whose only academic degree was a BA from NYU in history. He brings hope to us all. So nevertheless, he certainly, I think, is one of the last people for whom this is true. And in any case, he's also intimately involved with almost every important mid-century development in medicine, from the Salk vaccine to Kinsey's studies on sexuality, from low-dose carcinogenic efforts to try and figure out whether red dye number 40 will kill us all, to the regulatory scheme at the FDA for approving new drugs. He's the go-to statistician behind all these projects. But he's almost not known outside a relatively small group of biostatisticians, for whom he's one of the giants, but I would argue at least we should know more about him and what he's doing for this transformation in medicine. So just to give you a sense of where I'm going to go, I'm going to use 3 examples over the next part of the talk to try and argue, at least, for what we get when we put biostatistics back into the history of medicine. And then I'm going to step back to talk a little bit more about biostatistics in context, kind of broadly about mid-century quantification. And then I'll end with a few words on the promise of precision medicine or personalized medicine. So my first example, not surprisingly, for anyone who might be familiar with this, is the famous 1964 Surgeon General Luther Terry's Smoking and Health Report that established that, at least for men, there seemed to be a causal link between smoking cigarettes and getting lung cancer later. The general history of this report is actually fairly well known, and the general story is something like the following. At the population or epidemiological level, the association between smoking and lung cancer had long been established. It was generally known at the populational level, but it was very difficult at the individual level to show this causal relationship. And in particular, it was difficult using traditional laboratory or clinical means. So they would rub cigarettes on mice and tumors would result, but they didn't do that on humans. And they knew they couldn't actually do a randomized clinical trial assigning people, or children ideally, to smoking and non-smoking groups to try and actually figure out whether that would result in any statistically significant conclusion. So the committee that was tasked by the Surgeon General eventually settled on this idea of combining different types of evidence. So they said to judge or to evaluate the causal significance of the association, you needed to combine 5 different criteria: consistency, strength, specificity, temporal relationship, and coherence. And 3 of these, the committee found were relatively easy. So consistency was easy. All the studies suggested that there was an association between smoking and lung cancer. The temporal relationship was easy. People tended to smoke prior to lung cancer. They didn't tend to get lung cancer and then take up smoking. And then the coherence was easy in the sense the story, the biological story, that something you inhale into your lungs might in fact be harmful for those lungs, cohered, at least biologically. The problem was strength and specificity of this particular claim, and that's where they turned to statistical evidence. And the main statistical claim, don't worry, I'll walk you through this a couple times, is from Table 26, this very controversial Table 26. And the basic idea here is that you should use relative risk or mortality ratio. And in this way, you take the ratio of the number of observed deaths from a particular cause to the number of deaths you'd expect if smoking had no effect on that particular cause. So for instance, 1.7 mortality ratio for coronary artery disease means there's about 70% more deaths observed than expected. You'll note for lung cancer, there's a 10.8 mortality ratio, so over 10 times or 1,000% increase. And it was this that the committee controversially used to suggest that in fact this could be a causal claim. So this is the usual story, and it's I think, useful to start there. And the Surgeon General's Committee had been working on this for a couple of years. But what's often not discussed, at least in some of the accounts, is that statisticians had been working for this on a much longer time scale, how to make these kinds of causal claims. And as early as 1951, Cornfield in particular was working on this general problem of specificity. And the problem was that, according to the Surgeon General's own data, of course, there's a 1.68 mortality ratio with all causes of death. That is to say, just the very fact that you smoke has a 70% increase in all causes of death. And yet we know we don't want to start making causal claims for things like accidents or violence or cancer of the rectum necessarily, because those don't satisfy other of the criteria. And so he argued, in fact, that the problem is that it seems like it's strikingly non-specific in its effects, and in fact the strength, if you look at the pure number of deaths, is that there's 10 times as many deaths from coronary artery disease as there are from lung cancer. So he knew he was fighting an uphill battle in some sense, that the strength of the evidence seemed to point to something like coronary artery disease, and it was strikingly non-specific. And that's why he spent a decade arguing precisely for the mortality ratio, that even if the smokers were far more likely to die of artery disease than lung cancer, the relevant fact was that a smoker was 10 times more likely to die of lung cancer than a non-smoker. And that's the argument he had to make over the 1950s. This was, I think, some of us will agree, fairly uncontroversial, until you look at the history and find out it was actually incredibly controversial. So the review of the Surgeon General's report in the American Statistical Association Journal was strikingly negative, with K.C. Brownlee of the University of Chicago panning it, saying the statistical evidence was nowhere near strong enough to actually establish this causal relationship. R.A. Fisher infamously and strenuously denied any causal connection between smoking and cancer. And we know from Robert Proctor's work and elsewhere that some of these individuals received money from the tobacco companies, indeed, but most of the money actually came after 1965, which explains much less why the statistics, at least the statisticians, had much more of a beef with this kind of calculations prior to 1965. And to get a sense of these rival narratives, I want to use Joseph Berkson, the head of biometry at the Mayo Clinic in the 1950s and 1960s. And Berkson basically honed in directly on this question of the risk ratio, saying that people like Cornfield used it because it gave them exactly the answer that they were looking for. And instead, he thought the reason why something like the 10.8 mortality ratio was simply because the denominator was smaller. There's so many fewer lung cancer deaths that you're going to have these kinds of effects in rare diseases, and that we shouldn't look there for our evidence. And so he used a different one of the Surgeon General's tables, and he noted that the death rates from lung cancer paled in comparison to other diseases. And in fact, he also noted that the difference between non-smokers, light smokers, and heavy smokers, a kind of dose response for the act of smoking, seemed to also point to diseases like coronary artery disease rather than to lung cancer. That is to say, the difference in the absolute number of deaths increases both for absolute and for relative for these other diseases between the non-smokers and the heavy smokers. And he argued that this kind of lack of specificity, we might say, undermined any causal claims. As he concluded at the end of it, cancer is a biologic, not a statistical problem. Statistics can only play an ancillary role in its elucidation. But if biologists permit statisticians to become the arbiters of biologic questions, scientific disaster is inevitable. This from the head of biometry. So Berkson instead proposed, and this was common in the late 1950s, he proposed a constitutional basis. That is to say, perhaps people who are smokers, perhaps people who are non-smokers, are relatively light smokers, are a constitutional type that is biologically disposed, as he would say it, to self-protective habits, and that this is correlated generally with a constitutional resistance to mortal forces from disease. And this was his explanation for why you might see these kinds of associations. Cornfield replied directly to Berkson's article the very next year, or a couple years later, in 1959, when he co-authored it with a number of his colleagues, although Cornfield did all the statistical work there. And he argued again that the excess deaths, that is to say, the raw number of deaths, was useful, but it was useful only after causality had been established. That what you need to do first is establish causality, and then you can use the number of deaths to establish what he called the public health significance of the risk. Furthermore, Cornfield said his calculations provided an additional benefit, which is that if cigarette smokers have 9 or 10 times the rate of non-smokers of developing lung cancer, and you claim this is due to some other factor, then you have to show that that other factor among cigarette smokers is 9 or 10 times as prevalent as among non-smokers. That is to say, you can use the relative risk to put a baseline on the prevalence of any supposed third factor. And this was a very simple mathematical calculation. And he said for something like coronary artery disease with a 70% increase, it wouldn't be that hard to find something that was 70% more likely to be in a smoker than a non-smoker. But with lung cancer, with a 1,000% increase, you're going to be hard-pressed to find any factor that's not already known that's present in the population of smokers as opposed to lung smokers. He concluded a universe in which cause and effect always have a one-to-one correspondence with each other would be easier to understand, but it is obviously not the kind we inhabit. So the debate here wasn't about the quality of evidence. They were both using exactly the same data. The debate was about how statistics should enable you, or if statistics should enable you, to move from population-level association to individual claims of causality, from which the government could then find grounds for action. Cornfield had to work for 15 years, or nearly 15 years, to develop measures like the risk ratio precisely because they were controversial, precisely because his colleagues rejected them. My second case is involving the Framingham heart study, another paradigmatic mid-century associational statistics case for establishing causation. The Framingham's heart study started just after the founding of the National Heart Institute in 1949, and a group there wanted to study two of the most pressing problems of the heart at mid-century, namely heart disease and hypertension. And as has been well established, they developed a prospective study that would take place in Framingham, Massachusetts, a mid-sized city of a relatively homogeneous population, importantly that had only one major center where everyone got their health care from, so they could intervene at the major place everyone went for the clinic. And the idea was that they would take a random sample of all the adults in the city aged 30 to 59, and from that random sample, examine them every 2 years and examine them for their behaviors, their biomarkers, any other information they could gain about them, and on the basis of that, try and create a set of what they were calling by that point risk factors that would predict which ones of them would have a chance of early death or at least morbidity from coronary heart disease. This is a classic example, perhaps the example in some ways of a prospective study. The usual story about the statistics for this is that Dr. Thomas Dauber, who was the director of the Framingham Heart Study, essentially ran it with an iron fist and was not interested in having statisticians involved in his study. He wanted cardiologists and dietitians, not statisticians. And so the typical data they produced for the first 15 years was actually fairly simple. It showed relationships like this one, where on the bottom is the serum cholesterol level, and going up is the rate of, or the morbidity rate for coronary heart disease. The higher your cholesterol level, the higher your rates of coronary heart disease. By 1965, however, this study was coming under criticism because it wasn't justifying the huge costs that were involved in following up an entire population of adults every 2 years to give them exams. And influential epidemiologist Abe Lilienfeld was called in to try and provide advice to the National Institutes of Health, who was footing the bill for this study. And he tasked Jerry Cornfield with actually providing some recommendations to this study. Cornfield came in and he found the study was actually in shambles statistically. So for example, just to give a kind of simple example that Cornfield found problematic, he said, well, so far the study has shown that smoking cigarettes causes somewhere between half the risk of a heart attack and double the risk of a heart attack as non-smoking. That was the kind of evidence they had produced after 15 years of this follow-up data. And part of that is because heart attacks are rare. So no matter how many people you're following, you have to follow a lot more to be able to make these kinds of predictive claims about them. On the other hand, Cornfield said, for something like cholesterol, they've established this link so well in the first 10 years, there's no reason to keep funding the study. They know that it has a clear link. And so the study had this problem that either things were unclear or they were entirely clear. And instead, Cornfield said, we need to stop thinking of single factors. That's the problem that the cardiologists and the dietitians were using. They were trying to find a risk factor and a outcome and show a correlation. Instead, Cornfield said, the most interesting aspects of coronary heart disease are what he called multifactorial. That is to say, there's joint dependence between factors. And so the real question is not whether smokers have a high or lower rate of coronary heart disease in most cases. The question is whether somebody who, say, has high blood pressure and is overweight, whether stopping smoking will make any difference at all in their risks of coronary heart disease. And for that, you need to be able to combine the factors. What he noted is that part of the problem is that the statistics themselves were being used very poorly. So for instance, he noted if all you're interested in cholesterol levels, you can use a classification or a contingency table, a kind of classic N by N, J by K, 2 by 2 table to make these associations. And in theory, you could add as many variables as you want with this. So you could take the group of people who had cholesterol levels between 200 and 219, and you could classify all of them as either non-smokers or smokers, as overweight or as underweight. But the problem in the 1950s is that the bigger your classification and contingency tables you got, the bigger the matrix you had to invert would become in order to solve these equations. So he noted that if you only have 10 variables, and each of those only have 3 levels, you're going to be inverting a 59,000 cell matrix every time you're trying to solve your equations. And so he turned to an entirely different type of function that had been used for other purposes, namely discriminant functions. And the traditional use of this was in situations where you had 2 groups that had both previously been measured for some characteristic. You had a new candidate. You wanted to measure its characteristics and classify it or discriminate it into one of the 2 groups you knew something about. In short, what he wanted to do is discriminate into 2 groups, one of which would be a coronary heart disease population and one of which would be a normal population. This has now become standard practice indeed. But he's the first to actually try and apply it to a medical situation. He noted that the traditional model is linear in nature. It essentially comes from R.A. Fisher's work on irises. You can measure different species of iris, and then if I give you another iris, you can measure and try and classify it as one of the 2 species. And this involved essentially a maximization problem fitting a linear regression to these calculations. What he wanted to do instead was actually use probability. And so his insight was that we don't just want to know whether you're more likely to be in one population or another. We want to know whether your probability increases or not at being in the coronary heart disease population. And so he introduced Bayesian analysis into his calculation. Basically, instead of, I've put it here with the probability, the classic statement of Bayesian, and then all you do is instead of probability A given B, you just probability of coronary heart disease given the risk factors that you're expressing. And then the calculation comes out quite easily. And then you can use the data you've already collected from the Framingham project and actually come up with relatively simple equations here. This was one linking serum cholesterol to systolic blood pressure. And so calculationally, these are fairly simple. But in terms of using the statistics, this is an entirely new use of these kinds of methods that had been traditionally used more commonly for dose response curves for uncontrolled variables in experimental settings. And he said we should use the same statistics, in this case, for trying to predict whether people would belong in coronary heart disease populations. This, of course, enables you now to hold variables constant, to allow them both to change, whatever you want to do. And you don't have to use 2, of course, you can do many. But he didn't want to stress people out too much in his early writing, so he just stuck with 2, because people could figure that out. And of course, the reason to use cholesterol was precisely because he was criticizing the fact that the cholesterol use prior to him was so simplistic that you wouldn't have any idea what relationship cholesterol had to the systolic blood pressure in predicting coronary heart disease populations. This is, just for the record, for those of you who have never used this is exactly the same method that's used today. The numbers are a little better after 50 more years, but this is an online, I got this last week. This is an online Framingham risk score calculator. You can all do this right now. And you essentially will put in your gender, age, cholesterol. Now we distinguish HDL cholesterol. Smoker, your blood pressure, almost all the same things. Now we have to ask if you're on blood pressure medication. And of course, you get kicked out a score, a 10-year risk of developing coronary heart disease. So this has become essentially the paradigmatic model of how we think of coronary heart disease risk. And indeed, this same model has been used for a number of other diseases as well since this period. For my purposes, though, what I really want to emphasize here is that there was nothing that was immediately obvious about this use. And in fact, the Framingham Heart Initiative, despite being in the same institute of the National Institutes of Health as Jerry Cornfield, still did not think enough of statistics to employ him to use this kind of modeling in their own original, the first 12 years of the program. My final example that I want to is just the basic idea of clinical trials here. This one will be a little bit different in some sense. What we know about clinical trials between the 30s and the 70s is largely that they struggled to gain acceptance especially with a group of a population of physicians that was quite skeptical about control groups, about placebo groups, about the ethics of randomization in the question of treating individuals. And these kind of ethical questions are indeed, I think, importantly brought out in most of the work that's been done so far. The problem for me is that the treatment of statistics is essentially that you do the same thing as R.A. Fisher had done with his plants from the 1920s and 30s. And yes, there's been some formalization with Jerzy Neyman and Egon Pearson, as we know, and the kind of slight improvement, but it kind of do some hand waving. And essentially all you have to do is select a hypothesis, fix your level of type 1 and type 2 errors, you select a sample size, you randomize groups, you apply your treatment, you compare results, you publish a p-value, and you are done. And this mode of thinking about statistical trials that was formalized in this period actually bears very little resemblance to the actual statistical trials that were going on in the 1950s and 1960s. And I know this in part because the NIH was one of the major sites of early statistical trials. So they built an entire clinical center to actually run experiments, and it's part of the National Cancer Institute, on their new chemotherapeutic agents. And so it was one of the major initiatives at this, and these biostatisticians were indeed at the center of things. How do we know they're complicated? Well, take an early NIH trial, a famous example of one of the first fully randomized clinical trials in the United States, the retrolental fibroplasia trial, 1954. In this case, there was a debate about whether giving oxygen to premature babies would permanently blind them. And you can imagine, just with only that information, how tricky a study like that would be to design. Because on one hand, if you withhold oxygen to prevent blindness, you're likely to kill premature babies. On the other hand, if you give more oxygen, the traditional viewpoint is that you can't harm them at all, and yet you had this group that seemingly would be permanently blinded in every group receiving high levels of oxygen. And for someone like Cornfield, this is a problem, statistically at least, about early looks at the data, is how he would formulate this particular problem. That is to say, what you're tempted to do is to give high oxygen or low oxygen to maybe 10 babies or 100 babies, and you see what the effect is. You kind of check in on your statistics. Or perhaps there's a difference between male babies and female babies, or between overweight or premature babies, et cetera. But this poses a risk, Cornfield noted, to the entire edifice of traditional statistics testing, which is based on the idea that results are significant when they are rare. But the more times you run the same test, the more likely you will be, by definition, to find a statistically significant result. So he put it, again, in characteristically witty form. Just as the Sphinx winks if you look at it too long, so if you perform enough significance tests, you are sure to find significance, even when none exists. But repeated examination of results of a modern clinical trial is both necessary and desirable. So that's to say, this is the problem that statisticians were faced with. How can you actually design clinical methods, clinical trials, that will enable you to have early looks, but still preserve the structure of a statistically significant result? His first solution was to draw on sequential analysis, a relatively new field at this point, popularized by Abraham Wald and others. And for those of you who are unfamiliar, the basic idea is that you would take a look at the data after every pair of patients. So you would take a pair of patients, you'd randomize one to control, one to treatment, and then you'd see the results. And then you had three options. You can either decide the evidence is so good to accept A over B, it's so bad that you accept B over A, or you just do it again. And then you can do this after every pair of patients and continue on. The problem, Cornfield noted, with this particular method is that now the decision about whether one treatment is better than another doesn't just depend on the data. It depends on what he called the stopping rule. That is to say, the rule that you pick based on the significance levels you've chosen in order to run sequential analysis. So he said there could easily be circumstances where actually a disease, or a treatment, is uniformly fatal, and yet you're still going to have to kill the first 6 or the first 13 or the first 20 patients, knowing every time that that's what you're doing, in order to finally get your significance level to be to such an extent that you would accept or reject that particular treatment option. And he also noted the other problem with this particular method is that all trials that would reject the null hypothesis would be treated statistically as having almost the same amount of evidence against the null hypothesis. That is to say, you'd lump together really bad treatments with potentially marginally bad treatments and discard them all. And instead, you really want to know which treatments are kind of in the ballpark of currently accepted practice and which treatments are way out of the ballpark in this way. So he published 2 landmark articles in the Journal of the American Statistical Association and the American Statistician on precisely these theoretical issues of how we can move away from dealing with p-values, or at least we can be more flexible in how we use them. And so not only were the statistics not off the shelf in some sense, but actually the medical applications were driving developments in statistical practice itself as he was publishing this for statisticians more broadly. Over the following years into the 1960s, he popularized the term of relative betting odds for thinking of how to design trials under a Bayesian framework. Relative betting odds are essentially just the ratio of the posterior odds to the prior odds for a particular treatment effect. And so then you would turn the question of whether the observed data is unusual under a hypothesis, that's the classical frequentist question, into whether a particular hypothesis is more or less likely after you run your particular trial. And he said this sticks with what actual physicians think that clinical trials are for. They're for trying to figure out if a hypothesis is more or less likely after you've run it. So for Cornfield, at least as he described it, statisticians should be committing themselves to doing something other than feeding data into some gigantic algorithm and turning a crank on it. And instead, you should actually think about the ways the users, that is to say in his case, the physicians think about the statistics, and then design the statistics to match how they're actually going to be applied in practice, instead of simply using the statistics that you think are more mathematically interesting or appropriate and just trusting that the end user will use them in the same way. So I hope at least I've established in a kind of quick sense that statistical theory was not off the shelf. There is nothing that was fixed about this, and there's also nothing obvious about how we use statistics in these particular examples. And so what I want to turn now to is this question of biostatistics in context. And the first example I want to talk about is thinking more broadly about a disciplinary origin story for biostatistics. The traditional story, at least as I would argue, and it's conveniently emphasized by epidemiologists, is that the field of biostatistics emerges from the field of epidemiology, not surprisingly. In short, in the 19th century, epidemiologists are focused on infectious diseases, but once infectious diseases cease to be as of much concern after the 1930s and 40s, they turn their tools to chronic diseases. This is the classic explanation for why mid-century biostatistics uses some of the same tools as 19th century epidemiology. And while there are certainly some profound shifts in epidemiology in this period and in public health, I want to suggest at least the background of most of these biostatisticians suggests another direction. So for instance, you can think of someone like Cornfield, and Cornfield does not have the same background as someone like John Snow, a kind of classic epidemiological story. Instead, he has this degree in history. He got his first job working for the Bureau of Labor Statistics, in which he admitted that he joined the Bureau knowing nothing about labor or about statistics, but only that in 1933 he needed a job, and that was the one place that would be hiring in 1933. Nevertheless, his colleagues are all similarly trained in sociology, economics, agricultural, census sampling. None of them come from public health departments or epidemiology departments. None of them come from academic statistics departments, in part because very few exist at this point. So it's not really a kind of natural outgrowth for me, I think, from epidemiology. But if we look at their work, I also think there's a crucial difference with epidemiological work, at least as typically expressed in the 19th century. So let's take John Snow's example, this famous kind of story for epidemiologists that John Snow notices that there's a lot more cholera deaths near the Broad Street pump. He takes away the Broad Street pump. He notices cholera deaths go down in the same era. And then he essentially thinks his job is done, and he leaves it to the lab folks to isolate the bacterium that causes cholera. This is a bit of a caricature, nevertheless, stick with me. Or you can think of Joseph Goldberger, the other kind of classic public health epidemiology story from the early 20th century. He thinks that diet is involved in pellagra. He changes children's diets to try and figure out if diet actually is involved. He observes that children who are on better diets have lower rates of pellagra, and then he infers it has something to do with diet, and then he leaves it to the biochemists to figure out it is actually caused by a vitamin B3 or niacin deficiency. In this sense, epidemiology is a kind of initial, a kind of first step, looking at general rates, and then clinical or laboratory medicine would step in and actually determine causal claims. What I would like to suggest, though, is that this group of statisticians was not trained in this way of thinking at all, actually. That what they were trained in is what, at least in the late 1940s, was called social medicine, which is to say the idea that in the context of economic, environmental, industrial health, some of the biggest fields of the early 20th century, causal claims could be made from a much wider set of potential features in the environment, let's say, than simply a kind of one-to-one correspondence. So put statistically, most diseases aren't like cholera or tuberculosis or pellagra, which have clear, easily identifiable biochemical or biomedical causes that you can then act on. Most diseases aren't like that. And people coming from the economic, environmental, and industrial fields know this. And so they're much more prone to think more broadly about potential causes. Indeed, in a 1949 speech from then Surgeon General Leonard Scheel, he noted that his emerging statistics program at the NIH was really connected to a history of what he called environmental medicine and social medicine. Namely, it was explicitly a focus on multiple possible causes of disease, not a single-minded focus on isolating particular germs or microorganisms. The second particular claim I want to make is that Cornfield wasn't just working in a period of shifting roles for epidemiology, but a period of what we might think of as a fundamental shift in statistics itself, far beyond medicine. So for much of the 19th and early 20th century, statistics was treated as describing observations. So as Lorraine Daston and others have shown, experiment and observation have very complex histories. But suffice it to say that at least in the 19th century, you might think of them as kinds of opposites. That is to say, observation has a passive component, experiment has an active component. And indeed, for many of the early statisticians, so here I'm thinking of Adolf Quetelet, Francis Galton, Carl Pearson, Udny Yule, and others, statistics were treated as tools for dealing with observations. So Raymond Pearl famously called them technics or techniques. That is to say, they might help you interpret data, they might show regularities, they might enable measurement, but what they're not going to do is actually enable you to conduct experiments. And a major shift, I think, occurred, and it's not just me who thinks this occurs, in the 20s and 30s, with thinking of statistics as actually involved in the design of experiments. That is to say, instead of just having data that you apply your statistics to, you could actually be involved in designing experiments that would produce data uniquely well suited to be statistically interpreted after the experiment. And of course, this is, not surprisingly, the design of experiments by R.A. Fisher, 1935. And we can see the effect of this across the entire world of statistics. So I just use one example. I took Henry Garrett's Introductory Statistics in Psychology and Education, real page-turner, from 1926. And this didn't mention experiment at all. There was no mention of testing hypotheses, of running experiments, of designing experiments. But then by the time you get to the 5th and 6th edition, there are multiple chapters precisely on how you test experimental hypotheses. So the field of statistics has gone from a kind of accepting the data to actually being actively involved in producing the data over this time period. And I think there's a lot more to say here about psychology and agriculture and other fields. But for the purposes of medicine, at least, one of the things I want to say is that people like Cornfield were really honing in on this distinction traditionally made between observation and experiment and trying to demolish it. So Cornfield, for example, was invited to comment on this question of experiment in medicine by the American statistician in 1954, and here's what he described it as. He said, we admit that if we make an event occur, we feel really good about it. right? We seem to have controlled something by making something occur in an experiment. And when we simply observe it, it feels passive. But he says we need to reject these initial feelings. There are always lurking variables, whether we're treating them experimentally or observationally. And so he said to distinguish between statistical association on the one hand and relationships that are established by experimentation on the other, without any reference to alternative variables present in one case but not the other, seems to us to be neither good statistics, good science, nor good philosophy, though it may be good red herring. So we see this sentiment being enacted concretely in the development of what are called quasi-experiments and natural experiments in the late 1940s and early 1950s. They're coining these terms, or they're using a kind of term that was coined in sociology just a few years earlier, because they want to emphasize that actually the data that comes from smoking and lung cancer, that is to say generally retrospective observational studies, or Framingham, which is generally a prospective study, or clinical trials, they all have their problems. And the only question is whether statistics produced are useful to answering the questions at hand. The third context I want to talk a little bit about is a reason for this shift between broadly 1925 and 1955 of statistics into a discipline of experimentation. And I think one of the often overlooked aspects of this is actually the role of the Cold War more broadly. And I wish I could talk more about this. But what I'll simply point to is that as Paul Erickson and many others have started to look at in the early Cold War, sciences that were being funded broadly, including statistics, were focused extensively on decision-making in contexts of limited information. That is to say, how do you make decisions when the information you have is not just temporally limited, but essentially limited? And indeed, statisticians who were surveying the field were noting that statistics was uniquely positioned to serve just this role, because while it had traditionally been used to describe observations, now to draw statistical inference meant to actually talk about a reasonable course of action on the basis of incomplete information. And so Leonard Jimmy Savage's 1954 Foundations of Statistics opens famously with the statement that decisions made in the face of uncertainty pervade the life of every individual and organization. That's precisely why you needed statistics. And yet this kind of sentiment 50 years earlier would have not at all been familiar to working statisticians, that it's not about decision making, it's about describing observations. But yet this 1954 context is precisely the context in which Cornfield is breaking down the distinctions between observation and experiment in order to make a broader claim about the role of statistics in a world of inescapable uncertainty. And finally, I want to just say just a quick word about the history of quantification in this mid-century context. For a long time now, since the mid-90s and Ted Porter's landmark Trust in Numbers, we've tended, I think a little lazily, to talk about fields quantifying, that is to say, fields adopting numbers because they're weak and they want to become strong. They want to become objective, or at least look objective if they're never going to be objective. And this is a kind of move of weak fields to strong fields. And this might be true, but it has the problem that it's timeless. It applies just as much to 17th century life insurance as to 19th century asylum statistics. And I think the post-war medicine situation seems to me very different. After all, medicine wasn't weak in the post-war world. It was arguably as strong as it's ever been in an age of miraculous drugs and new vaccines. And yet this is precisely the period in which it quantifies more quickly and more extensively than any other period in its history. And I think the reason, at least as I see it, is that statistics are taken up by physicians and medical professionals precisely because it allows them to make claims of causality in a situation of inescapable subjectivity, that is to say both the patients and the doctors having particular biases, but also in inescapable uncertainty. That is to say, you will never have the same response to the same treatment, even in the same person at different times. And so the solution here is not to throw your hands up, but is actually to move from clinical laboratory research and expand the acceptable fields for making medical conclusions into statistics. And I don't think it takes too much to see these kinds of expansion of causal claims in our own world. And so certainly in machine learning, in neural nets, in sports analytics, in big data, all these depend on the ability to expand what is statistically possible, perhaps at the cost, at least some would argue, of a kind of interpretability or explainability in the data methods themselves. And I think there's an irony that one of the biggest disciplinary losers of the move to big data could be statistics themselves, with statisticians' petty concern about which models are most appropriate, and they're worrying about the formal requirements for statistical testing, as opposed to the dream that if you just get more data, these kinds of small concerns will all be washed away. But as I promised in my title, I want to just end with a word about precision medicine. And indeed, I think what we've done is set up precisely this world of precision medicine, the history of which is almost always told about the history of the Human Genome Project. And I think that's an important aspect. How could you not? And there certainly have been a development of successful pharmacogenetic treatments in the last 20 years that have taken a lot of the limelight for the development of this kind of medicine to treat exactly who you are, your own biomarkers, your own genes, your own lifestyle, your own behaviors. However, I think the history of precision medicine up to this point has been oddly silent on this salient role of the history of biostatistics for it. So the focus on genetics, while well-merited, I think has created a kind of blind spot. So I want to illustrate this by just taking a recent article from 2013, recent for us, at least as historians, on N-of-1 trials. So this is the rediscovery of the notion of a trial, where essentially you test medicines on an N-of-1, the same patient, to see which medicine works better for the one person who matters, the patient in front of you. And the history of biostatistics is all over it. So the first of all is that they come from biostatistics departments that didn't exist before this mid-century movement toward biostatistics. The journal would have an oxymoronic title to physicians in the 1940s, the Journal of Clinical Epidemiology. That wouldn't make any sense prior to this moment in which epidemiology and the clinic are said to be the same kind of process. The focus of the N-of-1 trial is precisely on the chronic conditions that are hard to treat, which was precisely the mode at which the biostatisticians in the 1950s were focusing. The effect is to use pragmatic decision methodology, which could essentially be plucked right from Cornfield's statement that you need to have statistics that's pragmatic and focused on making decisions, precisely this early 1950s mode. And finally, the recommendation, the takeaway, is that you need to have Bayesian and adaptive methods, which are precisely the methods that Cornfield was arguing for in the American Statistician and the Journal of the American Statistical Association. And my point is not the old saw, there's nothing new under the sun, although I think you could make an argument like that. But nevertheless, I don't want to make that argument. Rather, what I think we should do here is start to think more carefully about the structure of mid-century medicine, which enabled you to go from an N of 10,000 to an N of 1 as being precisely suited to an era that claims we no longer need the N of 10,000, we only need the N of 1. And that actually the methods of moving from an N of 10,000 to an N of 1 are precisely the same methods as dealing with the N of 1, but with no acknowledgement or very little acknowledgement of this historical trajectory. So in this sense, I think if we can recapture the rise of biostatistics at mid-century, we can do more than simply tell a better story about the history of medicine. In fact, we can reveal something fundamental at the heart of how we know today in 2019 about diagnosis and treatment and about disease and health in our particular world. Thanks very much.